This is a curved 3D object, a cylinder. Well, almost. Today we're exploring the fascinating geometry behind these three-dimensional shapes, starting off with a cylinder. The volume of a cylinder is just the base area, which is pi r squared, times the height. It's kind of like a circular prism if you think about it. Let me become small again so I don't hog up half the screen. Okay, the surface area of a cylinder is simply going to be the area of one face, pi r squared, the area of the bottom face, which is also pi r squared, times the circumference times the height, which is the lateral surface area. Okay, now we're moving on to cone. And cone is very similar to a cylinder, except it's got a pointy top. The volume of a cone, 1/3 pi r squared h. So just 1/3 times pi times the radius squared times height. And the proof for this is not that simple, actually. It involves calculus, but so I'm not going to prove it, but it's good. It's still really important to know this formula and also know the surface area of a cone is just pi r squared times pi r times the slant height, which is s in this case. And then we can calculate the slant height in a right circular cone, which is a cone where this thing is right. You can do that by just using Pythagorean theorem. In this case, it's going to be square root of h squared plus r squared, right? As you can see here. And there's also another really cool concept. It's the sides of a cone can be unfolded to form a sector. Basically, what that means is if I take a cone, I can make it into a sector like this. A circular sector. This is a cone, as you can see, or at least my best attempt to make one. And notice what happens when I unfold it along its edge. Along this edge, I'm going to just slowly unfold the cone. It forms a sector. So essentially, when you put these parts of the sector together, they form a cone, and when you unfold that cone, it forms a sector of a circle. Isn't that cool? So that essentially gives us some useful information because now we can easily that's actually how the surface area for a cone is derived, because this would be the slant height. The radius of this sector is just going to be the slant height of the cone, and then we would just have that it's just pi. We can easily derive the formula for surface area of a cone from this sector. Okay, and the angle of the sector, that will depend on the dimensions of the cone. If it's a more thin shaped cone, the sector angle will be a bit smaller, like this one. If it's a more wide, flat cone, then it will be more like the one I drew over there. Okay, now let's try this interesting example. An ant sits on the circumference of the circular base of a party hat, a cone without a circular base. I'm just going to draw the circle because it's a cone. And as you can see here, there's no base to it, so it's just the lateral part, basically. Okay, and this has radius 2 and height root 5. So radius to the height is going to be square root of 5. Okay, and the ant, it says the ant wants to reach, let's say the ant is here, and ants are black. Let's make all of this blue. Ants are black, and I'm not going to try and draw an ant, so this is my ant. Nice little oval-shaped ant. And the ant wants to reach a point diametrically opposite, so the ant wants to reach right here. So the ant, let's draw that in. The ant is trying to go till all the way there. But it's asking, but there's no base, right? So you can't just travel directly across like that. There's only the sides. So what is the minimum possible distance the ants need to travel? The ants need to travel along the side. Like if you have a cone here, there's no base to it. It's like this. There's no base to this cone. It has to go along the sides. There's nothing at the bottom. So how should we do this? This is actually a pretty tricky problem to do if you don't use this technique. Because you don't know what is the minimum. If you find some possible value, how do you know if it's the minimum or not? 3D is hard. So why don't we make this 3D problem a 2D problem? What we can do is draw the sector. Remember how I just showed you that there's a sector for every cone? Let's draw that sector. And boom, we've got a sector for our cone. Oops, that's not supposed to happen. Okay, and we're given that the height and the special properties of this sector is that we would actually have that the radius of this sector equals the slant height of the cone, and we would also have that this length of this arc over here equals the circumference of the circle. Now, if you can imagine visually, the reason that's true is because let's have my nice little cone here. I know it's such an amazing cone. The circumference at the bottom over here, if we unfold it, it corresponds to the arc over there. And similarly, we would have that the slant height of the cone. So if we imagine fold the cone again, this is a cone, right? The slant height, which is something like this over here, if we unfold it, it becomes this radius segment over here. The segment over here, when you fold it inwards, it becomes the slant height of the cone. If that makes sense visually. So the slant height of the cone, what is it? Well, we know the radius, we know the height. We can use Pythagorean theorem to find the slant height. So let's say slant height L, 2 squared plus root 5 squared, which is 5, equals L squared. 9 equals L squared. L equals 3. So the slant height of the cone is 3. So the radius of the sector is 3. Now we also know that this arc length over here is simply the circumference of this base. The circumference of the base, 2 pi r, r is 2, so 4 pi. And therefore, this length over here is also 4 pi. Okay, that's good. So what does that mean? Let's imagine we drew the full circle for this, not just a sector. What would its circumference be? The full circle would have a circumference of 6 pi. 2 pi r. 2 times 3 times pi. 6 pi. But it's only 4 pi, not 6 pi. And that's because this is not a full circle. It's some sector. So therefore, theta, which let's call theta the angle of this over here, the angle over 360 times the circumference of the full circle equals the length of this arc over here, 4 pi. And now we can divide by 6 pi to both sides. Pi's cancel. This becomes 2/3. So 2/3 equals theta over 360. Theta is 240. And as you can see, this is going to be 240, even though it looks nothing like 240. It is 240. So you know what? Now that we know this is 240, we can actually redraw it so we don't get any confusions because of this completely inaccurate diagram. Because we did not know the angle before we calculated it. But now we do know the angle. Let's redraw it to make it more accurately matching our situation. So 3. And then let's extend that all the way out there. So now it looks a lot more like a 240-degree angle, even though the circle is very circular, of course. Okay, so this is a sector of a circle with 240-degree angle over there. Just do that. That's 240. And we know that the whole thing is 4 pi, right? And we found the angle 240. But let's look at what we're asking for. We're trying to go from this point here to diametrically opposite point. And let's say that on the cone, we started right over here. This was the point we're starting at. this is the original point, a location of the ant, right there. And let's go back to this cone here. If we fold this into a cone, as you can see, it's a nice cone. The point that's over here, if we start over here, we're trying to go all the way to the other side over there. And on that net, that means going from here to the point that's the midpoint. We go from here to the point that's the midpoint of the arc, because the midpoint of the arc is the point diametrically opposite of it. And I'm hopefully trying to help you visualize what's going on here, right? Just to explain one more time. This point right here is where, let's say we have a cone like this. We start at a point diametrically opposite. So we start, let's say here. We start right here. And we're trying to go to the other side, which is here. And if you unfold that cone, this point is nothing but right here. The starting location is nothing but the corner right here. And the diametrically opposite point is nothing but the midpoint of the arc. So we start over here, and we finish at the midpoint. Finish. What's the shortest path to get there? To do this, the shortest path will just be a straight line, of course. You can draw a nice straight line. So what is this straight line distance? Now I'm just going to make a much better diagram using my tools, so it actually looks like a circle and not an egg, or I don't know what that is even. There, now it's this nice circle, and we can draw our center here. 3, 3, and we can make that white. So now it's a much better circle. I drew an even better one. There. This is decent now. So now the rate, remember we're trying to draw, this is the finish line, this is the starting point. We try to draw all important radii in circle problems. So this will be 3. And we're trying to find this distance. Remember how this whole thing is 240? So that means that each of these pieces, remember this, because this is the midpoint of the arc, this part will be half the arc. So this will be 120 degrees, this arc, and this arc will be 120 as well. And that means this angle over here is 120, and this one here is 120. Now, 3, 3, and we're trying to find this. And this is 120 degrees. This is a common 2D geometry problem, which we know how to deal with. Because it's 120 degrees, what we're going to try and do is drop the altitude to the base. And that will, because it's an isosceles triangle, these angles are both equal, right? Isosceles sides, so angles equal. And that essentially means that these two angles are both going to be equal as well, because the total sum of the angles in a triangle must be 180. And if two of the angles are equal, the third angle must be equal as well, right? Both of these triangles, the top one and the bottom one, contain a right angle and x, right angle and x. So the third one must be equal too. And we already found that this total was 120, so each of those pieces was 60. And it's a common strategy when you have this kind of 120, 120, 30 triangle. It's almost like its own special triangle category. It's common that it might be good to memorize that if this is x, then this opposite side is x root 3. And that's just because we convert it into two 30, 60, 90s. So 30, 60, 90 triangles, we've got 2 of them. So 3 is the length of the hypotenuse. This is 3 halves is the length of this one. So 3 halves root 3 is the length of this part over here. And 3 halves root 3 is also the length of the other part. So their total length from coast to coast is 3 root 3, right? It's the same property I just showed. So that's going to be our answer, because that's the shortest path. So this was an interesting problem, to say the least. The key ideas for this problem was the visualization aspect and breaking it apart into its net. And that was a bad diagram, but this was a good one. And then from here we saw that by my very well-designed cone, all we had to do was travel from here diametrically opposite. If we unfold that, we get that the diametrically opposite point if we start like here, we're trying to go here is a diametrically opposite point. And that means that we're just trying to find the shortest path from here to here. And that just becomes a simple 2D geometry problem. We use 30, 60, 90s, two of them, and get our answer. Now let's talk about spheres. So the volume of a sphere is 4/3 pi r cubed, the surface area 4 pi r squared. You have to memorize them. There's not an easy way to derive these formulas without using calculus. Okay, now let's solve a 3D geometry problem. And let me show you a cool little trick. Boom. Okay. Each of 4 spheres of radius 1 are tangent to 2 of the other spheres, such that all 4 of their centers lie in a plane. So if you can imagine, we essentially just have, if you have like a table, and then you place 4 spheres that are all next to each other in a square-like pattern. So 2, 2. And as you can see, this is a top view, and this is a side view. So all of the centers lie on a plane. That basically means that it's going to be flat. So it's something like this. All 4 of their centers form a plane. They're not like stacked on top of each other. They're all flat on the table, if you can imagine a table. And this is what the top view would look like in this case. So the 4 spheres are on the flat of the table, and if you're looking at the top view, it's just 4 circles. And we're asking for the radius of the smallest sphere that contains these 4 spheres. And I've drawn in the top view the black sphere, which is the sphere that contains all these spheres. It's the smallest one. And for it to be the smallest one, it has to be touching at all these points. And even so, all these points, it's tangent. The circles have to be tangent to the black outer circle. So this is the maximum configuration, because anything else, like this, would be bigger, right? The smallest one is when it's inscribed. All of the 4 circles are inscribed in this circle. How do we find the radius of the black circle? Well, the trick is, these 4 spheres all have radius 1. So 1, again, like I mentioned, a technique is draw all the important radii, connect the center to all of the points on the circle that are important, that are already defined. So you don't want to be drawing random radii like this, because that doesn't give you anything useful. But radii like this, there, you should draw them all, because they'll give you valuable information about a circle. 1, 1, 1. Okay, that's good. 2, 2, 2, 2. Wow, that's interesting, isn't it? That has all 4 sides equal. Cool. So it has to be a square, not just a rhombus, a square. Now the reason it has to be a square, not just a rhombus, is because over here, as you can see, it's a symmetric situation. All 4 of these spheres, they have the same radius, so it's symmetric about each of these sides. It's symmetric about each of them. So that means that each of these angles, they must be 90 degrees. So that makes it a square. And this is not a rigorous proof of it, but you don't need to find a rigorous proof, because this is not a proof contest, right? AMC, it's not a proof contest. Okay, so now we figured out that all of these angles, they must be 90 degrees, and that's because of symmetry, right? You can't have these angles being really small, but these ones being big. That makes 0 sense. So how should we find the radius of this black circle? First of all, what is the center of the black circle? The center of the black circle is right there. So the radius is just the distance from the center to one of the points on the circle. So now let's draw some of these black radii. As you can see there. Okay, maybe I'll just erase them for now, because I think it's cluttering up the diagram. Basically, we're trying to find one of these distances here. And how should we do that? Well, notice that this over here, we've already found this part to be 1. So to find the whole thing, we just need to find whatever this distance has to be. So how should we find that distance? the key idea here is to find that distance. Let's draw all four of these possible segments. Now this is, of course, just going to have a length of 2. All four of these segments have a length of 2 because 1 plus 1 is equal to 2. And let's draw that over here. Because the reason I'm drawing a separate diagram is it's a lot more confusing to see stuff when you've got 4 of the circles and a bunch of lines mixed in. So essentially, I'm just drawing the same diagram again. I'm drawing part of the diagram again. I'm drawing the center part, where we have all 4 sides are 2. And we're looking to find this part over here, which is nothing but this part over here. Well, notice that these two are bisectors. So, because the whole angle is 90, and because of symmetry reasons, both sides of the diagram are symmetric. So, these two angles, they must be equal. They have to be 45, so the total sum is 90. Similarly, we have that these two angles are 45, and by symmetry again, it's symmetric about this line as well. Top and bottom are basically the same thing. These two angles are also 45, and these ones as well. And look, by triangle angle sum, if two angles are 45, the last angle must be 90, because 90 plus 45 plus 45 is 180, and that's true for all of them. 45, 45, 90 triangles. So now we're looking for this length, right? So we're looking for the length of the part that connects the black center to the center of any of the other circles. So we're looking for something like this or this or this or this, which is nothing but that. So if we're looking for that segment, how should we even go about finding that? Well, we have to use the 45, 45, 90 properties. To find the length of that blue segment, all we have to do is see that 2 is the hypotenuse of the 45, 45, 90 triangle, and the hypotenuse is root 2 times each of the legs. So if this is something like x, then we have x root 2 is 2, x equals root 2. So that segment that we were looking for is nothing but root 2. And this is also root 2 as well, because it's the same thing. And that means the radius of the big circle is root 2 part plus the 1 part. So root 2 plus 1. And that is the answer for this problem. That's it. Because we're asked to find the radius of the sphere. Now, a question some of you might have is, we're dealing with spheres. How can we just assume they're circles? Well, essentially what we're doing is we're taking this cross section. So imagine we have 4 spheres just sitting on the table like that. What we're doing is we're slicing through the middle of all those spheres and all 5 spheres. And that is the diagram you see over here, the top view. And that is called a cross section. We're taking a cross section of a 3D diagram. And it's a powerful tool when solving 3D problems. 3D is complicated. Even for everyone, including me, it's sometimes hard to visualize when the situation is very complicated. Cross sections help make 3D problems 2D problems. So because we've got these spheres and all that complicated stuff, what we did is we took a cross section straight through the middle. So you can imagine 4 spheres. If a sphere is like this, you take it to the middle height. Like if there are 4 spheres sitting on a table, you go take the height that's you take it in the middle of the sphere, so the plane that passes through all 4 centers, and you take that plane, you look at the image on that plane, it will be this top view image. And then from there, it's just a regular 2D problem, which we know how to solve using our 2D techniques. Okay, let's now solve an extension of this problem from the AMC 12. 8 spheres of radius 1 per octant, are tangent to the coordinate planes. So we've got a 3-dimensional coordinate plane now. This is going to be an interesting problem. Draw our axes. So our axes will have to look something like this. It's a 3D drawing. and this is the origin, right? And we've got octants. And if you try to understand, this is not a two-dimensional, this is a three-dimensional axis. So we've got 8 spheres of radius 1, 1 per octants tangent to the coordinate planes. So that means is we have, let's say, one sphere that's sitting here in this octant, one sphere in this octant, and you know how there's 4 quadrants? When you add a third axis, now there's 8 octants. That's why it's called an octant. 1, 2, 3, 4, 5, 6, 7, 8. I know it's a jumble. That's why I didn't draw those spheres here. So 8 spheres, 1 per octant, and basically we're given that we're asked to find the radius of the smallest sphere centered at the origin, which is there, that contains all 8 spheres. Well, notice this is a very similar problem. Over here, we took the 4 spheres to be a square. Over here, what we're going to do is, instead of a square, now we have a cube. And we can imagine that each of these 8 spheres is centered at each of these vertices of the cube. There's 8 vertices of the cube. There's 8 spheres that are going to be there. Each one is centered at the cube. And they are tangent to the coordinate axes with radius 1. And if they're all tangent to the coordinate axes, that means they're also going to be tangent to themselves. So all 8 spheres, you can imagine them to be like, you know how we had 4 spheres on the table you can imagine earlier? Now imagine 4 spheres on the table, and then we had a second layer of 4 spheres on the table. And then now we have 8 spheres. Hopefully that you can visualize that. So now we imagine each sphere is centered at one of these vertices of the cube. And we're asked to find the smallest sphere centered at the origin that contains all 8 of these spheres. How should we do this? Well, the key thing to notice for this problem is that the radius of the sphere, well, there's a sphere centered at this corner and a sphere centered at this corner. You know what? Let's do those permanently, not using our disappearing tool. And there's, of course, some other spheres here, 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 which I'm not going to draw because those are not the important ones. So, again, imagine from here all the way till here, the smallest sphere that can wrap around all 8 of these spheres must go from here to here, right? Because it must cover all. This is the longest possible length of the 8 spheres. So to find if it's going to be a sphere inscribed in it, we must have that it goes all the way from here to here. So what that actually means is from here all the way till, let's not use red. From here all the way till here, that is going to be the diameter. And let me draw that a bit better. That's going to have to be the diameter of the sphere, similarly. Because that's the maximum distance between 2 points on of the smaller spheres, then that has to be the diameter of the biggest sphere, so it's as small as it can be. It's the biggest sphere, but we're asked for the smallest sphere that can contain them. So it's still the biggest sphere, it's just asking what is the smallest possible radius of this biggest sphere. So its diameter has to go from here to here, which means that it will pass through the vertex of the cube, go through the space diagonal, and then go through one more radii. If that hopefully should make sense. So it's one radius here, that's 1. Then it goes through the space diagonal of the cube, and remember, that's just root 3 times side length. The side length of this cube is simply going to be 2, right? Because one radius here, and then another sphere centered here, 1 radius. So side length of the cube is 2. That means the space diagonal of the cube will be 2 root 3. And if the space diagonal of the cube is 2 root 3, and then we also have this part over here is just 1, so then the total diameter is this part plus the space diagonal, 2 root 3 plus 1. That makes up the diameter of the biggest sphere. So 2 root 3 plus 2 is diameter of the of the sphere we're looking for. It's the biggest sphere, but we're asking for the smallest. Again, the reason it says smallest sphere that contains these 8 spheres. So it's the biggest sphere relative to these spheres of radius 1, but we're asking for the smallest possible sphere that does this, because there could be even bigger spheres like this, which just leave a lot of empty room for no reason. So this is the diameter of the sphere we're looking for. The radius will just be half that, so root 3 plus 1. Notice how it was very similar to the 2D case of how we had, or not the 2D case, the 4-sphere case of how we had 1, 1 here, and then the diagonal made up the diameter, right? We had a radius here, and then the diagonal of the cube, which is this part. And that combined makes up the diameter of the sphere that's around all 4 of the spheres. So in the 3D case, it's very similar. We have a cube, and the diameter of this black sphere is this 1 radius plus the space diagonal of this cube. And yeah, that's it for this problem. The answer is root 3 plus 1. And now we're ready to move on to similar triangles in 3D. We explored similar triangles in 2D, but let's step it up a dimension. We're ready to move on to tackling these tricky problems, but they can be solved using similar triangles. Click on the video right there.